Hello everyone, and welcome back to PLC Programming from Scratch. This is Section 4, Programming Fundamentals. And let's make sure you have a good understanding of everything we've covered so far in this course. If you don't, this next section is going to be more than a little challenging. Now we're going to get into a little bit more of the nitty-gritty behind the scenes of making a PLC work, controlling it, setting it up to run, and if you don't already have a solid understanding of what I/O is, what digital is, what analog is, then please go back to the previous sections, review them, and come back to this section whenever you're ready. And assuming that you already are and that you've been paying attention, let's get going. So the first thing we're going to look at is how does a PLC manage its own information, manage its own data internally? When we look at our RSLogix 500 programming environment, on the left, if we go to our navigation pane, under the program files, the next section is data files. And you might imagine that's where we're going to be storing all of the data. When you look at the data files, there are a lot of different options of what type of data the PLC can store. And just to give some idea, when I try to create a new data file, I have the choices of binary, timers, counters, controls, integers, so on and so forth, routing information, extended routing information. And the good news is you are not going to use all of these most of the time. 80% of what you do will be done with 20% of these options. That being said, there will be times when you will need to use some of the other ones, and I'm sure you'll have the opportunity to learn them as you go. For now, we're going to discuss the very basic ones, the ones that we're going to be using day in and day out in our programming lives, and those are binary, integers, and floats. Most of you probably already know the difference between those three. But as this is a novice course, we're going to go ahead and get into that a little bit. So if you want to go ahead and skip a little bit, you can, but I recommend sticking around just as a review if nothing else. I'm looking over into the data files again, and you see I have O0, I have I1, S2, the numbers correspond to the actual file, but the letters give us an idea of what the type is. So when we see B22 and B21 and B9, those are all bits. And bits are what the program uses to store Boolean information. And when you hear expressions Boolean, discrete, digital, those all mean the same thing. 0 or 1. And when we open one of these up, this is what the data table actually looks like. So we have, let's choose a bit, B300. This bit is 0. When we look at B301, right now the value is 1. All of these values will only ever be 0 or 1. That's what a bit is. So, as you might imagine, when we're looking at digital inputs and digital outputs, we're going to be using the bits, the B3s and the B9s and whatever other data files we want to add and create. And if I want to create a B52, I could do it. Not the aircraft, but certainly the data file. When we are looking at analog signals, we're going to be looking at N's and F's. N you might guess, stands for integer. So when we open up this data table, you'll notice our addressing is a little different. It's not B3:0/2. Instead, it's just N7:0, because now we're looking at the word level rather than addressing down to the bit level, but we'll get into that a little bit later. The next thing you might notice is when you look at the data table, you don't have zeros and ones exclusively. Yes, you do still have some 0 values and 1 values. You also have values like 30,000 and 4,993. An integer can handle a much larger value depending whether it's a 16-bit or a 32-bit system. But for most of the numbers that you'll be working with inside of a PLC program that do not have a decimal point, you'll be using integers. For those that do have or do need a decimal point, we're going to be using the F data files, floats. And when you look at the float values, as you probably would have anticipated, you have values like 63.35838. Now we have a lot more precision in a smaller range. So those are the 3 data tables that we're going to be using to store information most frequently. Now, everything you do in RSLogix 500 gets a memory address and a location. So even when we use a timer, we might not be using that timer, we might not think of it as storing information, but the PLC is storing information with a timer. It has to remember how long of a timer it is, when it started counting down, how much time is left, when it's fully counted down, when it's energized. It stores a lot of information. So even timers and things like counters are all going to have their own memory locations assigned. Alright, before we get into actual programming, we're going to take a little bit deeper look at the actual programming environment and get a little bit deeper into how a program actually executes. So we want to make sure we've got some of our terminologies consistent, and what we want to look at, first of all, we're looking at ladder logic. And just like a ladder, it has rungs. Each line of this program is considered a rung. And if you remember from earlier in the series, I had mentioned that other PLC programming languages were also based on ladder logic. Here's one example of another PLC programming environment, which you can see looks significantly different, but when you take a closer look, here on the left, you have a navigation pane. You have program files. To the right, you have a coding environment. And you see some of the same blocks and the same style of lines as you saw in the last one in our RSLogix 500. Here's another one. Again, you see navigation on the left. You see, even though it looks a little different, you have a basic ladder in your programming window. So once you pick up one form of ladder logic programming, it's really pretty easy to pick up on the rest. There are minor variations. Some have instructions, others don't have. Some call their instructions different things, but they really all work almost exactly the same way. So once you learn one, and RSLogix is a popular one, and it's a very well established one. Once you learn that, if you need to program a Mitsubishi or a Siemens or something like that, it's pretty easy to jump over and adapt what you know and be up and running in really a couple of days. While we're talking about RSLogix, we want to get back into just a little bit more program flow and terminology here in the program. Remember, a program file, when we talk about a program file, we're talking about a section of our program. that's being called independently from our main program file. So when we talk about program file 5, that's our alarms. And when we go in here, we have all of our program pertinent to controlling alarms. And we're going to get much deeper into alarms a little bit later in this series. The next terminologies we want to know are, we know what a program file is, what is a rung. And when you see these numbers on the left inside of our programming window, those are numbering the rungs. So each of these numbers correlates to a rung, even though it might have some extra lines going down, and some of those lines can become very deep and very complicated. But each of these numbers is a rung. What we have when we see it drop down and come around and maybe bypass something, that's called a branch. So we have program files to the left, the numbers represent rungs, and we might have multiple branches on a single rung. So if you look at, say, rung 2, you have 1, 2, 3, 4, 5, 6, 7. You have 7 different branches all on that same rung. So a single rung can be plenty more complex than 1 or 2 instructions, and it can certainly have more than 2 or 3 or even 10 outputs on that rung. So we need to have at least that understanding of what is a program file, what is a rung, and what is a branch before we move on. All right, everybody, we have one more short lecture before we get into actual programming, but this is something very critical to understand before we start trying to develop logic on our screen. When we look inside of our coding window, you might have already noticed this, but you generally have controls on the left and you have controls on the right and a big empty space here in the middle. And there is a great reason for that, and it's one absolutely fundamental and necessary to understand before going a single step further. The way ladder logic works, we already know it goes from, it runs from program file 2, and it calls the other programs and it jumps into them one after another one, and it runs from 0 down. But it's very important to understand that each one of these rungs runs from left to right. And why that's critical is because this giant gap here in the middle, all this white space on our rungs, divides our conditions on the left from our outputs, or you might think of them as actions, on the right. So imagine this program is running right now and it's scanning, and we're going to go step by step how the PLC is going to scan this program. It's going to come down here to 0, the rung 0, and it's going to look at this first condition. And remember, the things on the left are conditions. Think of them as if statements. If this is true, then this big white space represents a then, and what happens on the right is what it's going to do, but it's only going to perform these actions if these conditions on the left are met. If it comes to rung 0, it's going to look at bit T4:42/DN, which is an address for what's important to understand right now. It's just a single bit. And it's going to say, if that bit equals 0, then we want to come over here and do this thing. But if we come down to here and this bit is not equal to 0, the PLC is going to skip right down to rung 1, and it's going to say, okay, then is this bit equal to 1? And if it's not, it's going to say fine. And it's going to come down here. And it's going to say, is this bit equal to 1? If it is, it's going to perform this action. Then it's going to move down to rung 3. And it's going to say, does this bit equal 1? And if it does, it's going to do, again, top to bottom, it's going to perform this action, this action, this action, all the way down to this action before it goes to the next line. And here we have 2 conditions on the left, so it's going to say, is this one true? Yes. Is this one equal to 1? Yes. What about this one? Is this one equal to 1? No. Let's imagine that it's not equal to 1. Well, it goes on down to rung 5, so it will not perform these 2 actions unless both of these are true. And remember, it's going to run through this whole program in about 6 milliseconds. So if these 2 are true, it's going to do these things, scan the rest of the program, and come back around. And in that time, in that 6 milliseconds, maybe something has changed in the process or in the memory registers, and for whatever reason now, maybe one of these isn't true anymore. So the next time it scans, it won't do these things, and it'll just skip down to 5. So if you don't take anything else out of this lecture, the one thing you have to understand and you can't forget from here going forward, this is the one thing that makes ladder logic make sense, is what you see on the left are conditions. What you see on the right are actions. And for each branch, you have one action. If we want multiple actions to come out of this rung, we have to put each action on a separate branch. What we cannot have is 2 actions on the same branch. If we try it, the program's going to give us a hiccup, and it's going to say invalid output instruction position. What does that mean? You've got an output followed by another output, and that does not jibe. Once we put everything on its own branch, we're great. We can have 20 or 30 conditions, one right after another. That's great. The program loves that. Not a problem. But actions have to be on separate branches. Just remember, 1 action per branch, conditions on the left, actions on the right. And if every condition that's lined up on the left is not true, what happens on the right will be skipped, and it'll proceed to the next rung. The exception, and it's not really an exception, but you can think about it as an exception, is when you have a branch in your conditions. So when we get to this is true, but this is not true. It's not going to jump down to rung 5. It's going to try to take the branch, and it's going to say, what about this branch? Is this true? And if this is true, then it'll go ahead and it'll execute these 2 outputs. You can think of this ladder like an electrical schematic, where you have a hot wire over here and you have a ground wire over here, and your electricity is going to try to get to the ground. So if there's not a path on this top branch, then it's going to take the bottom branch and it's going to try to get a path to ground. If both of these aren't true and this isn't true, then it's going to give up looking for a path here, and it's going to go down here and see if these are true. And if these aren't true, it's going to go down to here. And if this is true, then it'll execute that and continue its search. That is how a PLC program works. That is a fundamental understanding of ladder logic. And as long as you don't forget that, you're probably going to do all right in the next few lessons. But in the next few, We're going to get into programming. We're going to start discussing different logical operations, various types of conditions, various types of output, and it is going to get a little more complicated. So something I said at the beginning of this section, if you haven't already learned the concepts, input, output, analog, digital, Boolean, float, integer, left to right, top to bottom, program files, rungs, branches, if all of those words don't mean something to you at this point, then I invite you to please go back and review a little bit so that you can get the most out of the following lessons, because we're about to dive headfirst into programming, and if you don't understand these fundamental concepts at this point, watching the next few lessons right now is really kind of going to be a waste of time, and a lot of the concepts are going to be lost. Take the time, go back, do it right, get the most bang for the buck, and when you complete this course, you will be ready to start writing PLC programs. Alright, it is that time. We are going to start looking at actual programming. We're going to start learning the programming instructions, and we're going to start learning how to create ladder logic. So in this first example, I'm using 3 different instructions, and these are 3 instructions that you will find in virtually every single PLC programming system in existence in the world today. And these are the most basic instructions in PLC programming. This first one that looks like an open set of contacts, if we look at the instruction type, it's called XIC. And XIC stands for Examine If Closed. What that means is, imagine this is connected to an input, like as I have labeled here, a light switch. And that light switch, if you understand how a switch works, a switch is either open or it's closed. It's either an open circuit or it's a closed circuit. And think of these contacts as representing that switch. Right now it looks like those contacts are apart, which means open. So it's not going to do anything. You notice if we're looking for a path to the right, we don't have a path unless this closes. So what happens when we close our light switch? Then we have potential coming across our rung, and what do? Well, obviously our light bulb's going to come on. What kind of instruction do we have? When we look at this instruction type, it's called an OTE instruction. And what OTE represents, I can't really say it stands for because it's certainly not a proper acronym, but it stands for Output Energize. So this is going to energize an output. What that really means is it's going to take some bit somewhere within our data files, and it's going to set that bit to 1, and it's going to keep that bit as a value of 1 as long as this condition is true, meaning as long as the switch is closed. If you look between these 2 instructions, you'll notice they have very similar addresses. This one is addressed B3:0/0. This one is addressed B3:0/2. Now, ironically, I could actually reverse those 2-bit addresses, and it wouldn't make any difference whatsoever. Because when you open the data file, and this one right now, it only has 1 word and it has all 16 bits, but I can just as easily modify that table, and let's go ahead and give it 20 elements so it looks a little more healthy when we open it up. In the program, in this data file, none of these bits really mean anything to the PLC. When I click on B378, it has no symbol, it has no description, it's meaningless to the PLC. It's just a bit somewhere in a data table. It's completely irrelevant. The only reason B300 is important is because I've described it, I've given it a description, and I've used it in the program. And because I'm using it, now all of a sudden it matters, because the rest of my logic is going to be looking at that address and say, hey, is the light switch open or closed? We know the light switch is connected to B300. So I will tell the program by putting blocks like this in there, check B300 to see if it's open or to see if it's closed. And depending, maybe we'll do an instruction to the right, maybe we won't. In this case, if B300 is closed, we want to go ahead and energize an output. And of course, we're going to have that address, B302, we're going to have that tied to an output, namely our light bulb. So, granted, you really don't need a PLC to control a light bulb, especially not if the only input that it requires is a simple light switch. Obviously, you can bypass the PLC with that circuit. But, just for demonstration's sake, we're going to say that there is a real input coming into our PLC from a light switch, and there is a real light bulb attached to an output on our PLC. And when you flip that switch, that light bulb should come on, and you can toggle it back and forth. There's a third instruction that we're going to talk about in this lecture, and if you look at the block, the instruction we're using here, you remember this is called an XIC, examine if closed. Well, we have a block here that looks very similar, and don't mind the green line, that is telling us that it's currently true in the data table. B301 is another address. It's right next door to our light switch, only this one we're calling a car door. And you notice this symbol looks exactly like this symbol, with one exception: it's got this diagonal line through it. And as you remember, this is an XIC, examine if closed. This one is an XIO, examine if open. So these two are really kind of opposites. When it refers to the data file, if this one equals 1, then it's going to say it's true, and it's going to go ahead and let it keep going and looking for the right. If there are no more conditions, it'll take this action. If we do have 2 or 3 more conditions here, it's going to consider this one true. It's going to move to the next condition to see if it's true, then to the next condition, and if everything's true, then it'll go ahead and execute. But back to these two. This one is going to be considered true only if B3:0/0 is equal to 1. As the opposite, B301 is going to have to be equal to 0, which means open, which means false. And as counterintuitive as that might seem, under that circumstance, this block is going to be evaluated as true. And in this case, I have a car door, and it's tied to an output over here, the ding 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 sound. Now what do I mean by that? Well, we're examining if opened. So what happens when we open our car door? Well, if we have a car that was built within the last 20 years, when you open the door, the car says ding 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 ding. And this is the logic for that kind of circuit right here. Examine if opened. Is the car door open? Yes. Go ahead and make the ding 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 sound, but we don't want to hear it once we close the door. That's what this circuit does. Now, if we wanted to modify this a little bit, and actually, let's just take that out, and take that out. So we're not looking at outputs. Now obviously this program wouldn't compile and wouldn't execute because we have to have some kind of action on each rung. But we're just going to focus right now on the two conditions, and I'm going to address these as the same thing. So assuming these are both tied to the light switch, stop and think for a minute. If I have an instruction here, an output here, and an output on this rung as well, will those two outputs ever execute at the same time? And hopefully you've concluded no, they won't. The reason is, when you look at our two conditions on these two rungs, we are looking at the same address, B300 and B300 again. Here, we're examining it if it's closed, meaning if it's equal to 1. Here, we're examining it only if it's open and equal to 0. Well, we're not talking about quantum mechanics. This isn't Schrodinger's bit. In other words, it can't be equal to 0 and 1 at the same time. It can only ever be one or the other. So one of these two rungs will always execute. It'll always be one or the other. It'll never be both, and it can never be neither. It always has to be one or the other, because a bit will always be equal to either 0 or 1, and only one of those two values. So those are the first three instructions that any programmer needs to learn. Output energize, examine if closed, and examine if open. And with those three instructions, you'll be able to do so much control and so much programming, it will seriously blow your mind how much you can get away with just using those three things. Now when it comes to energizing an output, and I'm going to go ahead and there's our light bulb. I'm going to go ahead and put that back just to tell you that there are other ways to energize an output, to energize a bit, to set a bit equal to 1. And we're going to cover those in the next lecture. But this is the preferred method. So anytime you want to change a bit from 0 to 1, you almost always want to use an OTE, an output energize block. There are other ways to accomplish that, but we're going to discuss a little bit more in the next lecture why you want to stick with OTE instead of OTLs. Hello folks, here we are back again and ready for our next big chunk of programming. This time we're going to look at another way to energize a bit, or to set a bit's value to 1. The last time you remember, we discussed this operator right here. That's the output energize. And just as a reminder, when we have some conditions on the left which are true, then this instruction, output energize, will energize that bit, and it will stay energized only as long as these conditions to the left are true. Once this condition becomes untrue, this bit will immediately de-energize. Well, now we're going to look at an instruction that works a little bit differently, and instead of OTE, now we have OTL. And you remember OTE means output energize. Well, OTL means output latch. The difference is, aside from the fact that you notice this has a little L in the middle, is when this condition becomes true, i.e. we close our light switch, then the light bulb will energize, but it will latch into that position. What that means is when we go back to the wall and we turn our light switch into the off position and we open that switch again, our light bulb will stay energized. And it will remain that way until we execute an output unlatch on the same address, in this case B3:0/2. So for instance, we might want to tie that to our light switch being open. So now when we close our switch, our light bulb latches into the on position, and when we open our switch, we unlatch our light bulb, forcing it into the de-energized or off position. Now, using this instruction in and of itself is not evil. Latching and unlatching is perfectly appropriate programming, and you see latch and unlatch commands in most programming systems. The problem that you see is a lot of abuse of latching and unlatching. Now we're going to get into a little bit of programming best practice. When someone first starts programming, they're going to have a tendency to want to energize, let's say, a pump. We're going to want to energize it in one program file that's dedicated to recovery, in another program file that's dedicated to warm up, in another program file we're going to want to energize that pump in 6 different places. And the RSLogix is smart. It won't let you energize the same thing in 3 or 4 or 5 different places, but it will let you latch and unlatch in several different places. Now, when you're writing a program, that might seem very convenient, but it creates a lot of problems down the road. So here is your best practice, and this is a lesson you want to learn today and remember for the rest of your programming life. You want to energize a bit in one place in your entire program. You never want to energize the same bit in 3 different places. So if you have your light bulb energized in ladder 2 and rung 5, then this is the only place in your entire program you ever want to energize that bit. You can look at that bit in a million different places. If you want to set conditions that if that light bulb is energized, then do something over here to the right of this rung, you can look at it, examine it if open, examine it if closed, an unlimited number of times and places throughout your program, but you only ever want to energize in one place. Now, here's why that is. The abuse of the output latch comes from people will latch the light bulb in 20 different places within the same program, in 3 or 4 or 5 different program files, and they will unlatch that same light bulb in just as many different places. Aside from that being extraordinarily complicated, there will always come a time when you need to debug your program, troubleshoot your program, modify your program, and when you try to figure out why did my light bulb just come on, you have to hunt down every place in the program that you're latching that output and try to figure out if those conditions were present when the light bulb came on. And some of these conditions come and go in one scan. In other words, once a light bulb energizes, 6 milliseconds later, the conditions that caused it to energize don't exist anymore. So even if you track down all the places where you're energizing the light bulb, when you look, the conditions aren't met, so you can't even tell where in your program it got energized. So it pops on, and you really don't have a way of knowing why until you go and start deleting lines of your program and running it again and trying to see when the light bulb stops coming on. And as you might realize, that becomes stupid very, very quickly. So if your light bulb is only ever energized in one place, that means it's only ever de-energized in one place. And anytime the light bulb is not working correctly, you come to ladder 2, rung 5, and all of your answers will be right on that rung. It's simple, it's fast, it's logical, and it is a best practice that you want to adhere to, as if your life depends on it. Energize one place and one place only. If you're going to use latch and unlatch, that's okay, but I would caution strongly against unlatching in multiple places or latching in multiple places. If you say, well, I want to energize the light bulb under 3 different sets of circumstances, remember, that's what we have rung branches for. And we drag a branch down here, and now we can put one set of conditions on this branch, another set of conditions on this branch, and both or either of those sets of conditions will energize your light bulb. You can extend the branch if you decide you want 3 different circumstances. You can extend it if you want 4. You can put 50 branches on here if you want that light bulb to come on under 50 different sets of circumstances. But you definitely want all of those to be on the same rung, and you want to energize your light bulb in one place. I think I've hammered this point enough. Right now you should understand the difference between output latch, output unlatch, and of course the better, preferred, recommended, traditional method of output energize. So assuming you've got that and you understand that best practice that a bit gets energized one place in your entire program, not in 2 or 3 or 4, you're ready to move on to the next section. All right, hold on to your hats because this next lecture is going to be a little bit tricky for some people to understand. What we're going to talk about this time is the one-shot, ONS. We're also going to look at the OSR, one-shot rising, and the OSF, one-shot falling. Now, so far we've been looking at bits, and it's been real simple. We energize the bit, we de-energize the bit. We check to see if the bit is energized, we check to see if the bit is de-energized. That is the basic element of PLC programming, particularly in terms of digital programming. But now we're going to get into a little bit more complicated instruction. Imagine for a second you're operating a push button, and you push the button one time. Well, when you push that button, for how long is that button depressed? Now, even if you press it fairly quickly, you imagine that button is still pressed for at least 1/10 or 1/5 of a second. Remember, our PLC can scan maybe once every 6 milliseconds. So if we're scanning that fast, when you push a button one time, how many times does the PLC scan? Well, I mean, theoretically, that can scan 20 times just while you very quickly push a push button. So if you want the PLC to do something one time instantaneously, to check a reading, to record a value, and you only want it to happen exactly one time when you push a button, how would you program that? Because when you push that button, the PLC is going to scan 10, 15, 20 times, and it's going to do that action that you only wanted to happen once several times over. And the answer is this instruction right here. It's called a one-shot. Now, right now, I'm introducing all of these instructions, and I know it's a little frustrating that you don't get to see them in action, and especially some of these things that happen instantaneously, it's a little hard to watch them. But we are going to actually see these things working on an emulator later on in the series, so bear with me. Right now, I'm introducing these instructions. I'm explaining them, giving you some best practices. You'll forget some of this stuff, but we're going to go through it 2 more times throughout this course, and by the end of it, you'll have a firm grasp of the concept. So right now, try to take it in, try to understand it, and don't worry, we are going to come back to it and get a little deeper into it. But for now, this is how the ONS, which means one shot, this is how it works. When the light switch gets flipped, whenever this block transitions from false to true, then the one shot changes to true for exactly one scan and one scan only. So whatever action is over here will happen one time during one scan, and then after that one scan, this one shot becomes false, and it remains false until this light switch becomes false and transitions back to true. So basically, when you have a one shot, everything to the left of it has to become true. And for every time it becomes true, the one shot will become true. Once it becomes false again, then the one shot will reset itself. And once everything becomes true, then it'll fire again and become true again for only one scan. So the way this line right here, we're just looking at rung 0, pretending that there is no rung 1, rung 2, rung 3. Just rung 0. The way this would work right now is if I walk over to the wall and I turn the light switch on, this one shot will become true for one scan, and my light bulb will light up for 6 milliseconds, which means I won't even see it light up. It won't even light up enough to produce light visible to the naked eye. And then this becomes false, so this remains de-energized. I turn the light switch off, nothing happens. And when I turn it back on again, mind you, I'm transitioning again from false to true, then my light bulb will come back on for an additional 6 milliseconds. Now, when you need something to happen only one time instantaneously, the one-shot instruction will do what you need, and you can use that 95% of the time in such situations, and it'll get the job done. But there are 2 other instructions that have a little bit more functionality, and they are available, albeit not in all programming environments. One-shots, you have those pretty much everywhere. When you get into some other processors and some other manufacturers, they won't have these 2. But just in case you do end up programming with RSLogix 500, or if you're using a system that has these, I'm going to go ahead and introduce them. They're a little bit more functional, but it does add a little bit of complexity to your program that just does not have to be there. So let's look first at the one-shot rising. Again, we flip our light switch from open to closed. So this block is transitioning from false to true. When that happens, you see this one-shot rising. Now, unlike the one-shot you see it on the left of the rung because it acts as a condition. It becomes true or it becomes false. The one-shot rising and the one-shot falling, on the other hand, you see them to the right of the rung. That means they're outputs. They're not conditions. These are actually energizing and de-energizing bits. So what happens with B305 and B306? When we flip this switch from open to closed and this becomes true, then we have our output bit, which works exactly like the one-shot. For one scan, it becomes true, and then it remains false until the next time this light bulb comes on. And actually, instead of the light bulb, let's go ahead and look at the light switch. That's better. Now, the B305 bit works differently. It stays on with the light switch until it's turned off. Just like the one-shot rising, we have the one-shot falling, which works on opposite condition as the one-shot rising. So again, we're going to sub that out with our light switch. The one-shot falling doesn't fire when the light switch transitions from false to true, when it transitions from open to closed, but vice versa. When we turn the light switch off, when this condition becomes false, then we instantaneously fire our B304 bit, which lasts for one scan and then de-energizes again, and our storage bit fires and stays energized until the light switch is closed again, in which case both of these become de-energized. So you have an extra sustained bit on your rising and falling. One works on a false to true transition, one works on a true to false transition. But the one shot, which is much simpler, only involves one bit and will give you the same one scan functionality as these two, will handle 90 to 95% of your needs. So when possible, stick with the one shot. If you absolutely have to have both bits, there's certainly nothing wrong with using one shot rising or one shot falling. I'm a fan of keeping it simple. There is one caveat that I'll add to the one shot, and that is that depending on the processor you're using, some processors don't allow you to have multiple instructions to the right of a one shot, and some processors don't allow you to branch around a one shot. So when you're programming with one shots, it's oftentimes simplest if you have one shot on each branch with one output, and on the next branch one shot and one output or one action. The last thing that I'll mention is, you see we're using an address here, B301, for our one shot. Again, you want to use one address per one shot, and you don't want to use that address for anything other than that one shot. So if you have 4 or 5 or 10 or 50 different one shots throughout your program, every one of them needs its own address. You can always refer to a one shot, but what you don't ever want to do is energize the same bit in 2 or 3 or 4 different places. Not only is it complicated, but it'll also add some very unpredictable and usually quite undesirable operation to your program. It's going to put a bunch of bugs in there, and people are going to think you don't know how to write a program. So energize a bit, one place and one place only. Every one-shot gets its own bit. If you're using a one-shot rising or a one-shot falling, they get 2 bits, and nothing else uses those bits. You can refer to them, you can check to see if they're open, you can check to see if they're closed as conditions for other logic. But what you don't ever want to do is energize either one of those anywhere else, i.e. use either one of those in another one-shot, a riser, a faller, or anything like that. And welcome back all. Now we're going to take it up another notch in complexity, and we're going to talk about timers. And it goes without saying that in process control, you want some things to happen after a certain delay, some things to start or shut down. You don't want to sound an alarm the second an errant condition occurs. You want to see if it smooths itself out after 3 or 4 seconds. Sometimes you want a warm-up cycle in a process for 15 to 30 minutes. There's lots of different reasons, lots of different things you're going to need timers for. So they're going to be a very big part of most of your programs. So we're going to look at a few of the common timers. And as usual, the first type of timer we're going to look at is the one that will do almost everything you need. There are a couple of other options for timers, and we're going to look at those as well. But the first one we're going to look at is the TON, which means timer on. And this is a little bit more complicated than most people would think a timer needs to be, but it's a good thing because the complexity's there, but that doesn't mean you always have to use it. So this is how it works. When we look at rung 0 in our program, of course our condition is our light switch 1, and I have a light switch 2 down here, so we're going to call this light switch 1 this time. So what happens is first it looks for me to have that switch in the closed or on position. So once I flip that switch, now we energize this timer. And we've got an address of T4:0, which correlates to our data table. And when we open the data table, we see we've got an EN bit, a TT bit, a DN bit, a base, a preset, an accumulator, a symbol, and a description. So there's a lot going on in that timer data file, and we're going to see what all that's about. The first thing is our time base, and when we look at that, we have some options of how we want to set our time. We can count seconds, we can count hundredths of a second, or we can count milliseconds. And unless you're really just using a time-critical application where milliseconds really count, most of the time it's just as practical to use seconds. So I've got here a preset of 5 of whatever this time base is. So if I have this set at milliseconds, then this is 5 milliseconds. But right now I have this set at 5 seconds. So this is a 5-second timer. And the accumulator is going to start accumulating time. In other words, it's going to start counting up once this condition is met and becomes true. Now on the far side of this timer, and these are all part of the block, you have an EN and you have a DN. And I'm not sure why it shows those two and not TT, but there should also be a TT down under here, but it just wasn't created as part of the block. It's just one of those things. But we're going to talk about all three, even if it's not part of the symbol. So here is how this timer works, and it's got a lot going on. Once we close our light switch, we energize our timer, and once it becomes energized, That's what this EN bit right here is. And as long as this light switch remains closed, this timer will always be energized. It doesn't matter if it's timed out, if it just started counting. If everything to the left of the timer is true, then the timer is considered energized. So when we come down to rung 2, we're evaluating T4:0/EN, and we're looking sure enough to see if that energized bit is energized. Well, assuming it is, our light bulb 1, 2 is going to illuminate. So basically, anytime light switch 1 is closed, light bulb 1, 2 will be energized. Okay, that's one of our 3 bits on this timer. The second bit is DN, and DN means down, short for countdown. So what happens, back to square one, our switch is open and we close our switch. And immediately our timer starts counting. 1, 2, 3, 4. Once it gets to 5, it's going to stop counting and this accumulator is going to stay at 5. Once it hits 5, it has counted down, so this DN bit is going to energize, which means when we come to rung 1, we're evaluating T4:0/DN. That's our down bit for timer 4-0. And once this times down, this bit is going to energize and our light bulb 1-1 will come on. This will stay down, this will stay energized, and this accumulator value will stay at 5 until one of 2 things happens. One, until this condition becomes false, in other words, we turn our light switch off, or there is actually a reset, RES command, that we can use that instruction as an output on this timer, and it will reset the accumulator and start over again. We're not really going to talk too much more about the reset, but that works on timers, that works on counters, and that's how the down bit works. So once it times out, it will stay timed out, and that down bit will remain energized as long as everything to the left remains true. And obviously, the energized bit will stay energized as well. Now we have this third bit, this TT bit, and TT somehow means timing. So back to square one, we flip our switch from the off to the on position, making this instruction true. Once we do, we already know what happens to our timer. It energizes, it starts counting. Well, once it starts counting, that's what timing means. So this TT bit is going to go ahead and energize, and our light bulb 1-3 is going to come on. However, once our accumulator gets up to 5, which is our preset value, now it's no longer timing. It has actually timed out. So now our TT bit will de-energize and our light bulb will go off, even though our energize and down bits remain on. So looking at all 3 of those together, when we flip the switch and we go from off position to on position, immediately our TT bit energizes and our energized bit energize. 5 seconds later, our TT bit de-energizes and our down bit energizes. Our energized bit remains energized because our timer's been energized all this time, so it doesn't de-energize. What we have then is the light bulb 1-2, which is tied to our energized bit. It's like it's tied directly to our light switch. When our light switch is on, light bulb 1-2 is on. When light switch 1 is off, naturally, light bulb 1, 2 is off. Our light bulb 1, 1 comes on a 5-second delay. So once we flip our switch, light bulb 1, 1 stays off for 5 seconds, then it comes on and stays on until we flip the switch off. Our light bulb 1, 3, when we flip the switch, it comes on, but it only stays on for 5 seconds, and then it shuts off. So that is how TON works, and those are the 3 control bits that work with TON. Now once you've learned TON, timer on, timer off is very easy to understand. Remember, timer 1 looks for the conditions on the left to be true, as do almost every other output in RSLogix 500. Timer off, however, is one of those freaky little exceptions. When this is true, this timer is de-energized. But once this becomes false, in other words, once we turn off our light switch, then the timer starts to count, and it has an EN and a DN and a TT bit. It's otherwise exactly like timer 1, only it works when the conditions are false instead of when the conditions are true. So if we have 2 sets of lights, set 1 consisting of lights 1, 2, and 3, and set 2 consisting of lights 1, 2, and 3, these 3 lights will come on when we turn light switch 1 on. These 3 lights, on the other hand, will come on when we turn light switch 2 off. So that's that. There is one other timer, and I didn't draw that out separately because it is basically exactly the same as TON, timer on, only this is a retentive timer on. It works exactly the same with one exception. When we're looking at our TON, when we turn our light switch on, it starts counting, and let's say it gets up to 3 seconds and we flip the light switch back off. Our accumulator resets to 0. Then when we turn our light switch back on, it begins to count again. And if we never leave our light switch on for 5 seconds, our timer will never time out. But anytime we open our light switch, anytime we turn it off, the timer will automatically reset without the use of a separate reset command. Retentive timer requires a reset. In order to reset the accumulator, you have to use a reset command. So if I turn my light switch on and I leave it on for 1 second and then I turn it off, this RTO accumulator will count up to 1 second and it will stay there. Even though my light switch is now off and my timer is de-energized, the accumulator will not reset. So when I turn it on again for another 2 seconds and then turn it off, now my accumulator adds those 2 seconds to the previous second that it was on. Now my timer is up to 3, which means once I turn my light switch on again in 2 seconds, this timer is going to time out, and it will retain that time until I use a reset command on T40. And once I energize that, then it'll reset the accumulator. But aside from retaining the accumulator value, RTO works exactly the same as TON. So your homework after this lesson is to study the timer a little bit and make sure you understand the operation of the DN bit, the EN bit, and the TT bit, the countdown, the timer energized, and the timer timing bits. The accumulator And the accumulator value and the preset value can also be changed from within the program, and they can be referenced from within the program. So that makes these timers very, very flexible, very, very useful. Alright, so after timers, we're going to look at counters. And if you made it through timers and you understood those, counters are going to be a walk in the park. So I've got our program in front of me, and I've got it revised a little bit. We still have our light switch condition on the left of rung 0, but now we've replaced our timer with a counter. In this case, we have a CTU, which is count up. There is also a CTD, which is count down. And I won't give an example of CTD, because it works exactly the same as CTU, only the number moves in a different direction. So it's pretty self-explanatory. So we have our CTU addressed as C5:0, and when you look over here in our data file, you see that C5 is in fact a default data file associated with counters, which is why it begins with the letter C. And I've arbitrarily plugged in a value of 10 for the preset. So we have an accumulator and a preset, just like we did on our timers. The preset told us how many units, whether it was seconds or milliseconds or hundredths of a second, we would be accumulating. Well, in this case, we are counting transitions. We are counting every time this becomes true. We're going to accumulate one transition. And obviously the goal is to accumulate 10 transitions. If you remember, we had 3 control bits for our timers. We had an energize bit, we had a done bit, and we also had a timing bit. Well, in this case, we have similar control bits. This time we have a count up bit, and we have a done bit. So each time this counts, the count up bit is going to energize. And since the count actually happens instantaneously, this CU bit is going to energize for about 6 milliseconds, meaning we're not going to get a lot of light out of our bulb if we have a light bulb tied to the CU bit. So I didn't draw that into this program. Instead, we're just looking at the done bit. So let's say this is our program, and we have our light switch on the wall, and I also had to put a reset button in because the counters require reset. So we walk over to our light switch and we turn it on, and guess what our light bulb does? It does nothing. Instead, our counter accumulator goes up to 1. If we leave our light switch on, it'll just sit there. It won't do a single thing until we turn that light switch off and turn it back on again. Now our accumulator goes up to 2, and at this point you've probably figured out I'm going to have to rock this light switch back and forth 8 more times before my light comes on, and that is correct. And when you're ready to turn it off, flipping the light switch is not going to help you. You're going to have to push the reset button, reset the accumulator on your counter, and the next time you want to turn the light on, better start flipping the switch. You've got 10 iterations to go. So that is the ins and outs of counters, and obviously those are useful for counting widgets traveling down a conveyor belt with a proximity switch, or counting how many cycles a machine runs. It can be used for hour meter programs if you're tracking runtime from within the PLC and you want to count how many hours have passed, how many days, how many weeks. A lot of uses for the timer, and the good news is timers and counters are so similar that if you understand one, the other almost becomes self-explanatory. As with any of these commands, it's good that you're getting introduced to them now, but you really don't master anything until you've used it, until you've practiced with it, until you've thrown it into a program, run it on an emulator, run it on a real PLC. So as soon as you get the opportunity, recommend, if you have a simulator or an emulator or an actual PLC available, put these commands on it, experiment with them. That's how you're really going to master all of these instructions. Let's take a break from the hard stuff and let's cover a bunch of instructions that are all pretty simple in one big shot. And we'll talk about one that's a little bit more interesting at the end. But you'll recognize the basic idea of this program from our last lecture. We still have our light switch. We're still looking for it to be closed or to be on. And we're still looking at our same counter, count up, and we're counting up to 10 transitions of that light switch going from off to on. Now, as we're flipping that light switch back and forth, we're looking on the following rungs at C5:0.ACC, and that is the address for this accumulator value right here. That's what the ACC stands for, is the accumulator. So as this C50 counter is counting up, it's storing that value in the accumulator. It goes to 1, 2, all the way up to 10, and we'll stay at 10 until we send it the reset command and send it back to 0, or in another way, overwrite that accumulator with a different value, which we can do logically, but we're not doing in this program. So for the intents and purposes of this program, there is no reset. There's nothing to overwrite the accumulator. We're just going to count up to 10 every time we flip the switch. And while we're flipping the switch, we've got a handful of light bulbs that are going to be coming on and going back off. And we're going to look at the logic. We're going to look at the comparators being used in the conditions to see why that is. So here we've got GRT, which means greater than. And it's nice enough to explain right below greater than and even show a symbol A greater than B. Then it explains source A and source B. So we've got source A set at our accumulator value for our counter, which is C5:0. And source B, I've plugged in an arbitrarily hard-coded value of 2. So what this is saying is when our accumulator is anything greater than 2, light bulb 1 is going to come on. So we flip our light switch 1 time, no light. 2 times, no light. But once we turn it on the 3rd time, we've got light bulb 1. The next rung down, on rung 2, we have a less than instruction. If you understand the greater than, you understand the less than. If our accumulator is 0, this light is on. If it's 1, if it's 2, if it's 3, light bulb 1, 2 will be on. But once our accumulator reaches 4 or any number greater than 4, our light bulb 1, 2 will be off. Moving down to rung 3, we have GEQ, which means greater than or equal to. And it explains that right below and even shows us the symbol for it. Naturally, we know how that works as well. I have a source B set of 6. If our counter's accumulator is 1 or 2, 3, 4, or 5, light bulb 1, 3 will be off. But once it hits 6 and stays at 6 or anything above, our light bulb 1, 3 will be on. And as much as we have a GEQ, we have an LEQ, less than or equal to. And see, like I said, you're learning a lot of instructions really fast, and these are all easy ones, but don't be mistaken, these are comparative operators that you will be using quite often, especially doing analog programming. So aside from greater than, less than, greater than or equal to, less than or equal to, we also have EQU and NEQ. Equals, not equal to. So if the C50's accumulator is equal to 1, then light bulb 1.5 will illuminate. And as long as our accumulator value is not equal to 1, light bulb 1.6 will illuminate. So when it's 0, we're lit up. 1, light shuts off. 2 comes back on and stays on all the way up to 10. So we've got greater than, less than, greater than equal to, less than equal to, not equal to. And now we have limit. And limit is a very useful comparator, and I'm going to teach you a secret about it that most of your seasoned programmers that have been doing this for quite a while do not know about this instruction. So that's your extra bonus for taking this course. You're going to learn something that the big dogs usually don't know. The way this works, it says here it's a limit test. So we're testing what? We're testing our accumulator value of our counter, and we're comparing it between a low limit and a high limit. So we've got naturally our low limit set at something like 4 and our high limit higher than our low limit. I set it at 7. Now this limit instruction is not exclusive, it is inclusive. And what I mean by that is it's like a greater than equal to combined with a less than equal to. So the accumulator doesn't have to be between 4 and 7. It can be equal to 4 or 7, or it can be between 4 and 7. And as long as that accumulator is 4, 5, 6, or 7, then light bulb 1.7 will be lit up. Now, here's the secret. It's intuitive that our low limit needs to be lower than our high limit, but what if we go and do something crazy, living on the edge, and we switch our low limit and high limit, so now our low limit is actually higher than our high limit? Well, off the top of your head, you would think that's not going to work. That's going to produce an undesired, unpredictable response. The program's going to generate an error, something like that. But actually, this works. And the way it works is exactly the opposite. It's basically reversing the polarity of the limit test. So now, if our accumulator is less than 4 or equal to 4, then our light bulb is going to come on. This limit test is going to pass true. If our accumulator is equal to or greater than 7, it will also be true. But if our accumulator is equal to 5 or 6, this light bulb will be off. So you can actually switch or invert the low and high limits on the limit test, and it will still work. It just works in reverse polarity. And most of your seasoned programmers do not know that little trick. So you now can teach them something that they will be surprised at and say, wow, where did you learn that? And of course you can point the finger at me. We are going to take one more lecture worth of easy instructions before we jump back into something a little more complicated. So now we're going to look at the basic mathematical operators. The first instruction we have on rung 0 is add. Add, obviously, is an addition block. So normally in a program you would not be adding two constants like this, and actually if you try to compile this program with two constants, it's not going to work because it won't let you do that kind of math. If you want to use constants, then you don't need to multiply 4 by 3 every single scan. You can just use the number 12 and be done with it. So normally you would have a memory address, an integer, or a float in at least one of these sources. The other one can be a constant, but at least one of these needs to be a memory location. But just to demonstrate, this is going to add 3 plus 4, and it's going to store it as this integer, or I could store it as a float. We also have a subtract block. Obviously, that subtracts source B from source A. So it's 10 minus 6. That's going to store the value 4 in the integer address N7:1. I don't think I have to spend a lot of time on multiply. That works the same way, as does divide, and divides 9 by 3. If you have a decimal and you're trying to force that decimal into an integer, obviously some rounding will occur. If you're storing it as a float, then you may or may not lose much precision. You won't lose much, but if you're using an irregular number, obviously it's going to have to truncate somewhere. Now, if you're doing any kind of halfway complex equation, call it the quadratic formula or something like that, you're going to have several math blocks, one for absolute value, and there are plenty more math blocks than what I'm showing. There's trigonometry, there's one that inverts values, there's several different mathematical operators, most of them just as self-explanatory as these. But the one that I want to call attention to here is CPT, which means compute. This one allows you to put in far more complex instructions, or I should say equations, with absolute values, square roots, factoring, all kinds of fun things. And it does it all in one neat, clean block. So when you're troubleshooting a program, when somebody else is trying to understand your program, they don't have to go back through 20 or 30 of these math blocks to try to figure out what your equation is. It's all right here, one block, doesn't take up space, and it stores the result just the same way these other ones do. The difference is you don't have to take the same value and cycle it through 100 different iterations, or even worse, use 100 different temporary values, all of which require their own location in memory, just to complete one calculation. That's insane. So not all processors have a compute block. Not even all processors that can be programmed with RSLogix 500 accept the compute block. But when it's available, it is a lifesaver. Okay, let's jump back into instructions with one of the slightly more complicated instructions to understand. And it's also one of the more useful instructions, particularly when you're bringing an analog signal in or sending an analog signal out. What this SCP, or scale with parameters, instruction does can be done with a compute block, or it can be done with various other math blocks all used in tandem. But this SCP is a lifesaver, and you will use it extensively with your analogs, so I want you to have a very good comfort level with this instruction. Let me show you how this works. You have several different things to address in here. So the first one, we are going to start with an input. Now that could be a number, that could be a signal coming in from an analog input, but for the sake of explanation right now, we're going to act like we're not dealing with signals or anything. We're just going to use a simple number. So I'm going to put a 2 in, and it's asking me what is my input minimum and maximum. So let's say we've got 2, and we're looking at a scale of 0 to 10. So we're going to put a 0 for the minimum and a 10 for the maximum. Now we're going to be scaling this 2. We're going to be taking it out of a 0 to 10 scale, and we're going to be translating it into a different scale. So let's say we're going to go from a 0 to 10 scale to a 0 to 100 scale. So our scaled minimum is 0, and our scaled maximum is 100. And our output would be saved to some kind of memory location, like an integer value of N710, for instance. Or actually, rather than call that result, we'll call that a scaled value. And what is going to do is this is going to take that 2 as an input, and it's going to save it as a 20 into the memory location N710. So it's taking 2 out of the 0 to 10 scale, and it's translating it to the corresponding value on a 0 to 100 scale, which would of course be 20. Now imagine for a second that we actually have an input coming in, and it's a 4 to 20 milliamp signal. So maybe the value that we have here is 6 milliamps or 5 milliamps, and we're going to put that, let's say we have a 6 milliamp signal, or 6 is our signal coming in, and that's on a scale of 4 to 20. And let's say that analog sensor is a temperature sensor that measures between 32 and 212 degrees. So we would put a 32 here, a 212 here, and whatever that actual temperature is at 6 milliamps would be saved into this memory location. And if we wanted a little bit more resolution, since we're trying to get a temperature on a small range, we would probably want to save that as a float instead of an integer. But we will get into why we would use a float and how that connects to the range and things like that in the next section when we briefly get into resolution and precision. But that is how our scale with parameters block works. It takes a value out of one scale, translates it into another scale. So for that 4 to 20 signal, if we wanted to translate that into 3 different types of readings, one as an integer, one as a float, one on a completely different scale, we could scale that same value 3 different times, saving it to 3 different places and using it for 3 different applications. So when analog programming, SCP, scale with parameters, can and most likely will be your very best friend. Alright, let's knock out one quick lesson. This is going to be on the MOV, the move instruction, and this is an easy one. What this does is moves a value from one memory register to another, and technically it really shouldn't be called move. Copy would be more appropriate, but there is a copy command already in the program and it does something completely different. So we're going to go ahead and go with it and roll with the punches, and we're going to say yes, okay, it's called move, but it really doesn't move something from one place to another. It really just imposes that value on a second location. So here I'm moving the source to a destination. My source, I'm just using a constant here, and I'm moving it to T4:0.pre. And if you remember what that is, a T4, that's a timer, and PRE, that's the preset. So if you remember a few lectures back, we were using light sets as an example, and we had a timer governing when lights would come on and when they would shut off. Well, that timer has a preset of however many of this unit, which right now I have it set as a second. So this is a 10-second timer, and that preset I have in here as hard-coded value. But if I execute this program, once this rung executes, it's going to move the value 20 into T4:0.pre, meaning this 10-second timer just became a 20-second timer. So that is one use of the move command. Another one is if you want to reset a value that's being used for math or accumulating days or hours and maybe an hour meter. If you just want to replace that value with a 0 or back to some default value, the move command is probably what you want to use. And there's one other usage of the move command, and that's what's called recasting. What recasting is when you're taking a value from one data type and you're converting it to another one. So in this case, let's say we have an integer value of N70 and maybe it's 25. Well, let's say we want to do some math with that value and change it to something that's going to end up with a decimal point. We won't be able to store that decimal value in an integer. So we're going to move that into a float. And now whenever we do additional math to it, like if we have a value of 7 and we want to divide it by 3, now we can store that decimal and we didn't lose any precision and we didn't compromise the integrity of our calculation either. Likewise, if we have a float and we want to round off the decimals and cast that as an integer, maybe we want to display that on a screen that is going to be for an operator who doesn't need to see a decimal, we can cast that float right back into an integer and display the value, and going back and forth between float and integer creates kind of a tricky method for limiting the precision of a float. So if we want a float that only has one decimal point, then we can multiply by 10, store it as an integer, divide it back down, and put it back into a float, and now we have a 0.1 or a 0.7 or something along those lines. So by going into an integer, multiplying by 10, and then coming back into a float, we can effectively round to the 10th place or to the 100th place if we want to multiply by 100, and so on and so forth. So there are definitely some instances where you'll have to do something like that and recast an integer as a float or vice versa, and the move command is good for that as well. Well, let's look at one more slightly complicated instruction set, and right now we're going to be looking at the jump and label, JMP and LBL instructions. And what these do is they allow the program to jump around instead of flowing normally like it does from top to bottom. So here's an example. We've got our light switch right here on B300 again, and we're looking for that to be closed. If it's closed, if it's in the on position, then our light bulb 1-1 is going to illuminate. And on this second branch, we're going to jump to location Q20. Now, any jump is addressed with a Q. The 2 has to be whatever ladder you're jumping in, and each label has to have its own number 0, 1, 2, 3 up through 15. So here we're jumping to program file 2 label 0. So we're in program file 2, which is easy because we only have one program file, and here's label 0, which is also easy because we only have one label right now. So if the light switch is on, then the light bulb is on, and when we scan this rung, we're going to jump straight to label 0, and we're going to keep executing from there. You notice we're going to be skipping rung 1 when we make that jump. And rung 1 has a horn bit attached to it, so we're assuming that's connected to a loud, annoying horn, which is going to get our attention anytime this light switch is off. Because if this light switch is off, the light bulb isn't going to be on, and we are not going to jump. Instead, we're going to go right down to rung 1 and sound the alarm. Then we're going to come down to rung 2 and we're going to jump to our label. Now, here's something strange about a label. If you have a label on rung 3 with whatever instructions here, you cannot execute this rung unless you jump to it. In other words, if you have a label on this line and there's no jumps anywhere on your program, it will never execute rung 3. It will go from 2 straight to 4. So in order to ever execute a rung that has a label, you must jump to it, which means you'll have your jumps and the logic that's possibly going to be skipped depending on the conditions above. But usually, right before your label rung, you'll have a jump rung just in case nothing above happens to jump to it. Then, as a last ditch, even though there are no conditions, you'll go ahead and jump to that rung unless it's something that you only want to execute under certain conditions. But that is the tricky part to remember the first time you're programming with jump and label, is everybody always puts in their jumps, puts in their labels, but forgets that the labeled rung will never execute unless you jump to it. So they have all these jumps with conditions, but they don't have a jump all by itself. So if none of the rungs with conditions are met, this line with whatever instruction might be to the right will never execute. So very important to remember that if you're using labels, you must jump to that line or it will never execute. Welcome to the last lecture of this section, and I know this has been a big section and a lot of material in here. Arguably, you could say that this is the heart of the whole course, and we're certainly going to go out with a bang. This last instruction that we're going to discuss is very important if you're doing any kind of very sensitive, very critical analog process control where you have to control an output to a very specific set point without a lot of drift and oscillation, rise and fall, things like that. So this is the PID control. PID stands for proportional integral derivative, and this is the math behind the instruction. So at a glance, unless you remember your calculus, this is not pretty, it's not easy to understand, and as difficult as it is for a programmer to understand, it's far more so for most of the programmers' customers, the machine operators at the end. So this is what is happening with this program and how this works, and I am not going to be able to give you a comprehensive understanding of the PID control in this course. The main reason being there are entire courses built around nothing but the PID control. There are $1,000 software packages that do nothing but make adjustments to the PID control. So what you should take out of this is the basic understanding of what it does and how it works when you need it. and you've got a lot of independent homework to do before you're probably ready to implement and tune a PID. But let me introduce it and let me explain it. Here, we're using a scale with parameters, and you see this address I:4.0. That is our imaginary input, and all of our inputs are going to begin with the letter I, just like our outputs are going to begin with the letter O. So we have an input signal, and based on the input minimum and maximum being 4,000 and 20,000, that tells us that we're working with a 4 to 20 milliamp signal. And why that comes out to 4,000 and 20,000 I will explain in the next section. So bear with me, and except for the time being, it really is 4,000 to 20,000. We're going to be scaling that to a range of 0 to 16,383. And if you don't already know resolutions and powers of 2 and bit depth and things like that, that number is going to seem very arbitrary and very strange. But again, next section, that number will come home and make a lot more sense to you. So right now, we're scaling this input signal from 4 to 20 to 0 to 16,383. And we're storing it in the integer location N70. Now, our next rung 1, the only thing we have happening here is our very unassuming, innocent-looking PID control, but we're going to see just how complicated and crazy this thing really is. We are storing it to PD, which is our type of data file over here. This is one that I had to create, so I created this PD22 and set it up for our PID control. And we have a process variable and a control variable. What a PID does is it receives a set point. That can be a hard-coded value, but more likely that's something that comes from an operator. That value tells it what set point it should try to maintain on the control variable and the process variable. So what this control looks at is N70, which is set up right now as its process variable. It looks at that and tries to adjust the control variable to make the process variable line up with the set point. And when we look inside the setup, we've got inverse or directly proportional control modes, whether our PID control is auto or manual. There are ranges as far as if we want to limit our minimum or maximum output, what our scale values are, our set point. There is just a whole lot going on inside the PID, and most of the adjustments that are going to dictate how this works occur on the KC, TI, and TD, your gain, reset, and rate. There are so many techniques, so many programs, there are so many different ways to tune a PID loop to keep it from oscillating, to tune it to maintain a set point accurately and correctly, and it's a course in and of its own. But right now, aside from being exposed, seeing it laid out in a program, and I want you to have a general idea of what the PID does and when you'll need it. If you are controlling a motor and its speed needs to be very precisely 2400 RPMs, and you have a tachometer sending you an analog input signal and you're sending an output to a motor drive, you can't afford for that motor to be oscillating up to 3,000 down to 2,000 and waving back and forth, it's going to destroy the drive, the motor, and probably your process as well. In that case, you're not going to be able to use simple logic to control that drive. You're going to have to use a PID control. And in that case, again, you're going to have some homework to do, but I want you to know that's the control you need to go to. That's the process that you're going to have to work through in order to tune that. And without being hooked up to a live motor with a live input signal coming in, you're really not going to be able to tune that loop. Even the emulators that are made by Rockwell, the same company that makes this software, the emulators won't even execute a PID control. When you run the PLC program through an emulator, it just ignores that PID and won't start it, not in manual, not in auto. So it's not the friendliest, easiest command to use, but when you need it, there is no substitution, there is no imitation. That's really what you have to use, and getting them set up right is never simple, particularly when the process is something very precise. So with that, I'm going to step away from the instruction, and we're going to get into a little bit more details on considerations and other aspects of the PLC programming process. But with the instructions that we've covered in this section, you're going to be able to do 90 to 95% of everything you need to do behind your computer to make a PLC control a process. Congratulations on making it through Section 4 of PLC Programming from Scratch. I know that section was not easy, particularly if you're brand new to PLC programming and logic and ladders and all of those things. Before you go to the next section, if this is new to you, then I would strongly recommend you go back through Section 4 one more time and refresh yourself on all of those instructions, and especially the different data types. You really want to know what is a float and when do you need to use one. What is an integer? What is a bit? What are the different values that those data types store? You probably don't know everything about addressing the bits and the integers and the floats yet, but that's one of those things that comes really once you start creating logic. Otherwise, the B3:7-5s and things like that, they just don't make a lot of sense until you really get into the data tables for yourself. By now, you should really understand the flow of a program. You should understand how the PLC scans each program file and each rung, and how it looks to find a path to the outputs. All of the program instructions that we touched on in this section, I know there are some of them that we didn't get very deep into, and for every one that we covered, there's 20 that we skipped. And that's okay, because again, this is an introductory to intermediate course, and we're trying to give you the 20% that you need to do 80 to 90% of the programming out there. So don't worry about the things that we didn't cover. Just make sure that you understand the things that we did. And particularly, we ended on a tricky note with that PID control loop, and that's not one that anybody's going to pick up very quickly until they've actually loaded it up, put it to use in a real-world scenario, and worked on tuning it. It's just not something that a person will ever learn out of a textbook or from a course, but it's something that you do need to be familiar with, and we are going to look at again a little bit later in the course. In the next section, we're going to jump into setting up a real working program from scratch. So up to this point, you've seen me show you code that I had already put into the program and maybe drop in a control or two, but we haven't really created a new program setting up and configuring the PLC, setting up the I/O modules, and that's the sort of thing that we're going to be doing in the next section. So you definitely want to be up to speed on everything we've covered before you go further, and trusting you have already, I'll see you there.